So now that we have our basic identities that we get to just accept are true, we're going to use them to prove something else. We're going to try to prove that 1 minus cos squared x is always equal to sine x times cos x times tan x, no matter what number I put in for x. I'll actually keep these on the screen. Now, in order to do a proof, so whenever I'm proving, the first thing I'm going to do is separate the left and the right-hand side. I do this to make sure that I don't just start moving things across the equal sign. If I do that, then I'm assuming that it's already true, and you can't do that if you're trying to prove that it's true. So I'm going to separate these out, so I'll put over here my left side. The left side of the equal sign is 1 minus cos squared x. And then I'll leave a bit of a space. And the right side of the equal sign is sine x times cos x times tan x. So if you don't like the fact that there's no times signs in there, you can put brackets around each of those ratios. Or you could put little time signs. Be careful they don't look like your x's. All right, so our job is to try to change both of these sides, or maybe just one of these sides, so it looks like the other. So we want the left side to look like the right side to prove that they're always true. There's a bunch of little tricks that you can use here to try to simplify things. When I look at this, what I notice is that the left-hand side only has cos x. It doesn't have any sines or tans. So that's a little troublesome, because when I look at the right-hand side, it's got sines, coses, and tans. The first thing that you can do when you're looking at these problems is whenever you see tan x, you could get rid of it by replacing the tan x with sine over cos. And that's going to get it all down to sines and coses on both sides. So because the left side has no tan x's, I can't use that trick. But on the right-hand side, I can replace the tan x with sine x over cos x. So I'm just using those little dots as multiplication signs. You'll find that as you go up into your upper year mathematics, we use dots instead of little x's like you did in elementary school. Dots mean multiplication. So I've replaced that, and now I can start working away at simplifying some of the stuff that I see on the right-hand side. What I see is it's all multiplication on the top, sine times cos times sine again, and then on the bottom it's just a cos. So hopefully you remember back to your chapter on rational expressions or rational functions, that if it's all multiplication, that means it's factored, and I can cancel common factors on the top and the bottom. So I have a cos x on the top and a cos x on the bottom, and I can cancel those out. So that leaves me now with sine x times sine x. So it's the same thing being multiplied twice. That's like sine x all being squared. And remember, our shorthand for that is to write sine squared of x. So that's kind of nice. I've really tidied up the right-hand side here. It does look a lot smaller, but the left-hand side still doesn't match it. So now what I'm going to do, because there's squaring, is I'm going to think about my Pythagorean identity. My Pythagorean identity uses sine squareds and cos squareds. So I'm hoping to use this identity to help me out. Now I can either look at the left side or I can look at the right side and work with either one of them. So just to show you that you don't have to stick with one side, I'm going to move over to the right-hand side here, and I see 1 minus cos squared of x. And what I remember is that I could rearrange this blue equation. I could move this plus cos squared over and subtract it from the other side, like I did on this line. I ended up with 1 minus cos squared. But we said that's the same as sine squared of x. Remember, we looked at that graph. We know that that's true. So I can replace 1 minus cos squared with sine squared of x. That's one of my identities. And now what I have is that the left-hand side looks the same as the right-hand side. And that's how I've now proven that this really is an identity. And if I were to graph this original expression, 1 minus cos squared x, and graph sine x times cos x times tan x, they'd be the same graph. And that means no matter what number I plugged in for x, I would get the same answer. So to summarize what I found, I'll say, look, now I've proven that the left side is equal to the right side. And that tells me that 1 minus cos squared x equals sine x times cos x times tan x for every single value of x. Except there's one restriction here, and my restriction, so I'm going to put a comma here because there's a restriction coming. My restriction comes from any denominators. Now, there were no denominators on the left-hand side, but when I look on the right-hand side, I created a denominator here when I replaced the tan x with sine over cos. So that tells me that cosine of x, that denominator, cannot equal 0 because I know I can't divide by 0. So I'll just state that restriction there. And they did remind me to do that in the question that said to state restrictions. All right, so we're going to try another example. This time we're going to prove, and we're using alphas. It looks like little a's here, but that's the little fish alpha. It says prove that tan squared of alpha, all being divided by 1 plus tan squared of alpha, is actually the same thing as sine squared of alpha. So we're going to set that up. We're going to separate. Remember, whenever it says prove, I need to separate the left side from the right-hand side. So the left side is equal to tan squared of alpha over 1 plus tan squared of alpha. And the right-hand side is equal to sine squared of alpha. Remember, this is just like a little puzzle, right? We have to try to change both of the sides or one of the sides so that they match. So we just keep playing around with it until we find something that works. Now, there's lots of different places that you can get started. You might want to change the sine squared. So you might go up and take a look. We have another expression for sine squared. Or you might be looking at those tans and thinking, I want to replace those tans. So I'm going to start with replacing the tans. It's a good rule of thumb if you don't know where to start to get rid of the tans and replace them with sine over cos. So I'm going to rewrite this first because I know that I'm turning those tans into fractions and I already have a fraction. So that's a little bit messy. What you can do is rewrite the fraction tan squared alpha. Instead of putting it over the denominator, I can say I want to do tan squared alpha divided by 1 plus tan squared of alpha. And that's the same as over, right? Dividing. And now what I can do is replace. So instead of tan squared alpha, I know that that means take tan and square it, right? When I put the squared on the inside, it means take tan and square it. But instead of writing tan of alpha in here, I'm going to go up and remember that tan of x is the same as sine of x over cos x. So I'm going to replace tan of alpha with sine of alpha over cos of alpha. And then in my second bracket, I'm going to do the same thing. I'm going to replace the tan squared alpha. That's going to be the same as sine of alpha over cos of alpha, and then all of that is being squared because all of tan was being squared. It got a little messier here. This isn't really helping. Remember that the whole time I'm thinking this is a puzzle. I need to make this whole big mess look like this. So my goal is to make this whole big mess look like sine squared of alpha, sorry. So now what I'm going to do is bring those squarings into the fraction. Don't forget when you're squaring a fraction, that means you square the top and square the bottom. So this is the same as sine squared of alpha over cos squared of alpha. And I'm dividing by 1 plus sine squared of alpha over cos squared of alpha. Okay. Still not great. We're still trying to make this simpler. Remember, our goal is to make this look like sine squared alpha, or take a break, go over to the right-hand side and work with that. So now, in order to divide, I've got a fraction. I want to divide it by this bracket. I'm thinking about bedmass. Bedmass says I have to simplify the stuff inside the bracket first. So I want to add this fraction plus 1 In order to add fractions, I need to change this one so that it has a common denominator. So I'm going to leave everything else the same. So all this stuff is staying the same. And now what I'm going to do is replace the 1. I want it to have a matching denominator as co-squared. That means I'm going to multiply the bottom by co-squared alpha and multiply the top by co-squared alpha. So co-squared over co-squared of alpha is going to be equal to 1. Just replace that. That's the same as saying, like, if you take 2 and you divide it by 2, that's equal to 1, right? As long as it matches top and bottom, you're going to get 1. All right, now that I have matching denominators or common denominators, I can add that stuff in the bracket. So the first part stays the same. And I'm dividing by, this time I'm going to add that stuff in the bracket. On the top here, I've got co-squared alpha plus sine squared alpha. And then on in the denominator, it's just co-squared of alpha. Okay, so we're getting there. Now I'm always taking a break and thinking about, what am I trying to get to again? I'm trying to get to sine squared alpha. And I'm always taking a look at the identities that I know I'm allowed to use. I can replace tans with sine over cos. I can replace sine squared plus cos squared with 1, or I can rearrange those things. And I can always get rid of cosecant, secant, or cotangent and replace those with the primary trigs. So what I'm noticing here is sine squared plus cos squared equals 1. And down here at the bottom of our question, we have cos squared plus sine squared. But that's the same, right, as sine squared plus cos squared. You can rearrange that. And the order doesn't matter when we add. So this numerator is equal to 1. And I can replace that. So I've got sine squared alpha over cos squared alpha. That first thing's still not changing. And now my numerator here is equal to 1. I'm using that Pythagorean identity. Don't forget to keep writing those alphas. Sometimes I see people forget to write the variable as you go. All right, this is better. This is getting better. It's getting smaller again. Remember, our goal is to get sine squared of alpha. So we're trying to think, okay, now what can I do with this puzzle? I've got a fraction divided by a fraction. And I know how to divide fractions. I leave the first fraction the same. Oops, alpha. I flip the second fraction, or take the reciprocal, and change the operation to multiplication. Don't forget, as soon as you have multiplication, you can cancel common factors top to bottom. So on the bottom here, I've got cos squared. On the top here, I've got cos squared. They cancel. And I'm left with sine squared over 1 times 1 over 1. And that's just equal to sine squared, which is our right-hand side. That was our goal. It took a lot, but we got there. Therefore, the left-hand side equals the right-hand side, and therefore, we know that our expressions are equal. That means that tan squared of alpha over 1 plus tan squared of alpha is equal to sine squared. Now, when I look at that denominator 1 plus tan squared of alpha, I need to make sure that that's never going to equal 0 because that's where my restrictions come from. But remember, if I'm taking tan of alpha and squaring it, no matter what the number is for tan of alpha, even if it's a negative, after I square it, it's a positive. So I have a positive number, or maybe 0, that's the smallest it can get, and I add 1 to it. Well, that means that the whole thing is never going to equal 0. It's going to be at the very smallest equal to 1. So I have no restrictions here because that denominator cannot equal 0. Okay? And I'm all done that question.